We just watched the video of the guy inside the car getting struck by 800,000 volts of lightning. The guy inside the car was perfectly fine. He was a little scared. I would be too. The car itself was perfectly fine. Why is that the case? Today we're going to go through a few things that lead us up to the answer to that question. Why is it safe to be inside a car, or any other metal conductor for that matter, and get struck by lightning? First, we have to define a term, static equilibrium. We talked about that a little bit in Physics 20. Static equilibrium is a point where things reach where the forces balance. If you have extra electrons on something, extra electrons on a conductor, not on an insulator. Everything we talk about today is going to be for conductors, not for insulators. If you've got a bunch of extra electrons on a conductor, then those electrons will all apply repulsive forces on each other. They're going to move around as a result of those repulsive forces. But at some point, those forces will become balanced. The charges will distribute to the point where those forces equal out and balanced. Those charges then stop. They don't move anymore. That's static equilibrium. And that's what charged conducting objects want to do. They always want to reach this point of static equilibrium, and they will eventually. Extra charges on these objects will eventually always reach a point of static equilibrium, a point where all the forces are balanced and these charges don't move around anymore. Let's look specifically at a few different scenarios of conductors that carry excess charges. The first scenario that we're going to look at is when we have a solid conducting sphere. Take a look at the diagram, the first one over on the left-hand side here. We have 3 extra electrons in this conducting sphere. So we've got this, it's like a marble, except it's made out of steel or copper or some kind of conducting metal as opposed to glass, like a typical marble is. 3 extra electrons. We're not suggesting that there's just 3 electrons. We're saying that, look, if there's 1,000,000 protons, there's 1,000,003 electrons. If there's 1,000,000 electrons, then there's 999,997 protons. There's 3 extra electrons. Now, those 3 extra electrons are just wherever. Okay, right now, they're drawn on the inside of this. Okay, they're somewhere close to the middle. Each of those 3 electrons will experience a force as a result of the other 2. Let's label them. There's charge 1, there's charge 2, there's charge 3. Charge 1 will experience a force of repulsion caused by number 3. Charge 1 is pushed to the left by number 3. We'll call that F31. Charge 1 is also pushed down this way as a result of charge 2. We'll call that F21. Now, where do those 2 forces combine to give me? What kind of force do those 2 forces combined result in? Force that's somewhere in the middle, right? A force that is down and to the left. Make sense? You got a force this way, a force this way. The net force caused by the 2 of those is going to be somewhere in the middle. Let's take a look at the forces caused on the other ones now. The force acting on number 2 is caused by number 1. The force on number 2 is caused by number 3. The net force on number 2 is this way. And similarly for number 3, we've got a force caused by number 2 this way, a force caused by number 1 this way. The net force acting on number 3 is this way. Let's erase all those red lines just to declutter it a little bit here. Now we've got just the net forces acting on it, these green forces. All 3 of these green forces acting on each of these 3 electrons point outwards toward the surface. Where are each of these electrons, these extra electrons, going to go? If there's a force upward, a net force upward on charge 2, where's charge 2 going to go? It's a simple question, guys. If there's a net force acting upward on charge 2, where's charge 2 going to go? Upward. Charge 1 is going to go down and to the left. Charge 3 is going to go down and to the right. In other words, charge 2 is going to go to the surface. Charge 1 is going to go to the surface. Charge 3 is going to go to the surface. Now, why don't they go beyond the surface? They stop there, at least normally they stop there. Why? Why don't they just keep going? There's still a force acting outwards on them. Why don't they keep going beyond the surface and actually leave this charged object? No, no. The reality is sometimes they do leave the object, but usually they don't. Why don't they? What's this solid conducting object usually going to be inside of? What's usually surrounding this conducting object? What's surrounding us? Yes, yes it is. What's surrounding our skin? Air. It's usually going to be air that surrounds this conducting sphere, right? Air is N. Starts with an I. It's an insulator. The electrons want to go further out. This electron wants to keep going. This one wants to keep going. This one wants to keep going. But it doesn't have much of an opportunity to keep going because it's on a conductor. It doesn't want to go into that insulator. Does that make sense? So they usually stop at the surface. Now, if you get a whole bunch of extra electrons on the surface, then sometimes they do leave and go into the air because the charged object, this conducting sphere, can't hold them all. There's only a certain number that they can hold. The more electrons you have on there, the stronger the repulsive force, and the more likely they are to leave this charged conducting sphere. But if you've got a reasonable number, they're going to stay on the surface. Charges that are in excess, electrons that are in excess of the number of protons, in other words, extra electrons, will always go to the surface of a conductor. Always. Now, what's the distribution look like? Take a look at the right-hand diagram here, diagram B. What's the distribution look like? Looks like these charges are equidistant apart. If you have a solid conducting sphere, two things will happen to the excess charges. One, they'll go to the surface. Two, they're going to be evenly distributed. That's when they've reached static equilibrium. They're going to go to that point, and at that point, the forces are balanced, so they're not going to go anywhere else. Does that make sense? All right, you can copy that down now. Don't copy this one down either yet until we're finished talking about it. This one's a bit of a different scenario. This time we have a solid, flat conducting plate. So not a sphere at all, but rather just a solid, flat plate like the meter stick I have in my hand right now, except it's metallic so that it's a conductor. What happens here? Let's take a look at the first diagram. We got 3 excess charges again. I mean, we could have 30 million excess charges. The same analysis would apply. It's just easier to draw it with 3 charges than it is with 30 million. Okay, same thing applies though. First charge has 2 forces acting on it. There's the force of 2 on 1 that acts to the left, right? 2 repels 1 to the left. It pushes it to the left. And there's the force of 3 on 1. It also pushes it to the left. So the net force here acting on number 1 is to the left as a result of number 2 and the result of number 3. Now there's also a force on number 3. First one's caused by number 1. It pushes number 3 to the right, and 2 pushes 3 to the right as well. But that net force is quite a bit smaller than the net force acting on number 1. Anybody want to take a stab at why that's the case? Force on number 1 is a result of 2 and 3. Force on number 3 is a result of 2 and 1. Why is the force on 3 significantly smaller than the force acting on number 1? Dylan? Good. It's farther away from charge 2. 1 on 3 is the same as 3 on 1. But 2 on 1 is quite a bit bigger than 2 on 3 because 2 is closer to 1 than it is on 3. So the force on number 3 is quite a bit smaller than the force on number 1. Let's take a look at the force on number 2 now. Force on charge 2. There is a force to the right caused by number 1 on 2. 1 pushes 2 to the right. 3 pushes 2 as a repulsive force pushes it to the left. Why is the force of 3 on 2 smaller than the force of 1 on 2? Once again, it's because 1 is a lot closer to number 2 than 3 is. So the force to the right is bigger than the force to the left. What's going to happen to that middle charge, charge 2, as a result of those 2 forces acting on it? It's going to go what? Good. It's going to move to the right. As it moves to the right here, and this is the critical point here right now, as charge 2 moves to the right, these two forces change in magnitude. What's going to happen to this force, the force of 1 on 2, as it moves to the right? It's going to get smaller because 1 and 2 are getting further apart. What's going to happen to the force of 3 on 2, this one that pushes it to the left? As it moves to the right, that force of 3 on 2 is going to get what? It's going to get bigger because 3 and 2 are getting closer together. At some point, the force of 1 on 2 will get small enough and the force of 3 on 2 will get big enough that those two forces will be the same value. They'll balance each other. What's going to happen to that charge, charge 2, after these forces balance each other, after they become the same value? It's going to stay there. Where is that going to happen? In the middle. Right? So charge 2 is going to go to the middle as a result of these forces that are acting on it. Remember what we said static equilibrium is? Remains at rest because forces are balanced. Well, it's not remaining at rest right now, but it will. As it gets pushed to the right, at some point, the forces will be balanced, and this charge is going to stop and remain at rest. It's going to stop and remain at rest when they're equally spaced. The bottom diagram is exactly the same as the middle diagram, except that you've got these little blue lines. What do you think these little blue lines represent? Not the force, but you're close. It's another F word. The field. I'm glad you said that one. It's the field, the electric field. Of course, the electric field points toward a negative producer, right? All right, you can copy this one down now. Let's take a look at our next scenario then. This one looks tricky. Don't write this yet again. Let me draw a couple things and explain a couple things first. Specifically, I want you to look at the first diagram here. I'm going to cover up the other ones right now. First diagram. We got 4 excess charges on this. This is an irregular shaped object. It's not uniform like the last two we had. First one was, remember, a uniform sphere. Second one was a uniform flat object. This is kind of pointy. This is kind of like your finger. And you walk across the carpet, walk up to somebody, stick out your finger, and you shock them. Okay, that's kind of what this is like. It's like the lightning rod on the top of a building, pointy. 4 extra charges on this, 4 excess electrons on this. We're going to label them once again 1, 2, 3, and 4. And we're going to focus on charge 2 right now. Charge 2 experiences a few forces here. The force of 1 on 2 is this way. They're both negatively charged, so it's a repulsive force. 1 is going to push 2 out this way. There's a force of 3 on 2 as well. 3 pushes 2 this way, away from charge 3. The force of 3 on 2 tells us why this extra charge, charge number 2, is going to be pushed to the outside. It gets pushed to the outer surface because there's a force outward and there's no force inward. So of course it's going to be pushed to the outside, just like it was in the last 2 scenarios that we've drawn. The solid conducting sphere and then the plain flat conducting plate. It gets pushed to the outside, pushed to the surface. But what about the distribution of it? In the last 2 examples we did, they were evenly distributed on the surface. So they're going to be evenly distributed here. Well, it's a little bit more of a complicated analysis here. Let's draw 2 components. 2 components of that F32. Even though we're not strictly dealing with the x-axis and the y-axis, we'll call this one the x and this one the y. There's a force F12 that pushes this electron out to the tip of this pointy surface. There is an x component of F32 that pulls it back. Which force is bigger, F12 or the x component of F32? F12 is bigger. So what's going to happen to this electron? It's going to go to the surface because of the y component of F32. Forget about that. We know it's going to go to the surface. Where's it going to go on the surface? F12 is bigger than the x component of F32. It's going to go to the right. So it's going to go closer to the tip. As it goes closer to the tip, F12 is going to decrease in value. F12 is going to get smaller. So at some point, the x component of F32 and F12 will balance each other. That's when the electron stops. That's when it's in static equilibrium. But this time it's not stopping when they're evenly distributed. It's stopping when these electrons have a higher concentration toward the point. That's why when you walk across that carpet, charge yourself by friction across that carpet, and you reach out and you go to touch somebody, you can shock somebody with your finger, but you can't shock somebody with your hip. Or you can't shock somebody with the side of your arm. Or you can't shock somebody with the side of your face. You can shock somebody with your pointy fingertip, because your pointy fingertip has a higher concentration of charge than the other parts of your body do. Does that make sense? Put your hand on the static ball, the Van de Graaff generator, which we did when we first started this unit. What happens? Well, the electrons are pushed, for the most part, to the parts of your body that are pointy, which is primarily your hair. Your hair gets extra electrons, a higher concentration of electrons, higher buildup of electrons. That makes them like charge. That makes them repel each other. They push each other apart. Your hair stands up on end. That's why buildings have lightning rods. High buildings have lightning rods. That's why lightning rods are pointy as opposed to spherical. Pointy objects build up charge better. They will either discharge a lot easier than rounded objects, or they will accept electrons, have electrons discharged to it a lot easier. The pointy objects have a higher concentration of charge. The charges still go to the surface, but it's a higher concentration at the point. The last two diagrams you see pretty much just explain the same thing. The third one, finally, is just showing the final distribution with the electric field lines pointing inwards. Okay, of course they point inwards. Look at the electric field strength here, though. It's not a uniform field. It's more uniform over here. They're almost parallel. But over here, the field lines are closer together at the point than they are as they get a little bit further out. It's a non-uniform field now. Field lines are not equidistant apart. They're not parallel to each other. Let's take a look at our next scenario. Now, this next scenario is really, really similar to the first one we had, where we had a solid conducting sphere. These ones are hollow. Okay, they're conducting spheres, but they're hollow inside. Now, the charge distribution is going to look remarkably like it did in the first case, where we had a solid conducting sphere. They're going to go to the outside, and they're going to be evenly spaced. So why are we drawing this? Why are we doing this one, the hollow conducting sphere, if it's exactly the same as the solid conducting sphere? I want to show you one more thing in this one that I didn't show you in the solid conducting sphere. And that is the electric field inside this hollow conducting sphere. You can see that the electric field outside points towards it, as it should, right? It's a negatively charged object. The electric field points toward a negatively charged object. But let's take a look at the electric field inside. The electric field caused by that first negative is towards it. The electric field caused by that second negative is towards it. The electric field caused by that third one is towards it. What do you think combined those three electric fields pointing in different directions give me? You got one up and to the left, one up and to the right, one straight down. They're going to combine to give me zero electric field. They add up to give me nothing. If I looked at the angles and I looked at the magnitudes and I did my x and y components and I added everything up, the total x component of that field would be 0. The total y component of that field would be 0. That tells us that the net electric field inside this hollow conducting sphere is 0 newtons per coulomb. What are the implications of that? Well, if there's no electric field inside this, then there's no effect, no electrical effect at least, on anything inside it. In other words, if you're inside this and there's a whole bunch of extra electrons on the outside due to maybe you rubbed it with rabbit fur, maybe it gets struck by lightning. There's a whole bunch of extra electrons on the outside. You are perfectly safe because the net electric field inside is 0. Does that make sense? That's why you're safe in a car in a lightning storm. It's what we call a Gaussian surface. A Gaussian surface, a surface in which the net electric field inside is 0, because although there are electric fields, they combine to cancel each other out. The charges all go to the outside. The charges on the outside produce a net electric field inside of zero. I was golfing a few years ago at a place in Calgary at, can't even remember what course it was, and I remember every 3 or 4 holes they had this, it was like this metal sphere kind of off to the side of the tee box, and it was like this doorway in it, and I remember thinking at the time when I first saw it, well, why do they have this? Like, what's the purpose of this? And then it struck me a little bit later on, if there's a lightning storm, what do? You go inside, and you're perfectly safe inside. Now, the flaw with that is that it didn't tell you. Like, it didn't have any signs. It didn't say, go inside here in a lightning storm. It just had these things. Now, most people are going to run as far away as they can from the metal object, right? Intuitively, inside a metal object is the last place you want to be in a lightning storm. The reality is it's the safest.